All right, we're going to be taking the derivative of a rational function, but instead of using the quotient rule, we're going to use the product rule. So we have this rational function f of x is 1 minus 5x over 1 plus 5x. And to use the product rule, which is a little bit more accessible than the quotient rule, I've always felt, we can strategically rewrite this original function. So what I'm going to do is that denominator is raised to the positive first power right now. I'm going to bring the numerator along and rewrite my denominator as 1 plus 5x raised to the negative first power. Now we've set ourselves up that it fits into the same pattern we have in the product rule over here, where we have two functions multiplied together. So I'm going to refer to this as f and this as g. As I'm looking at taking the derivative of f, multiplying it by g, and adding the original f multiplied by the derivative of g. You can kind of ignore that the original function was also named f. I'm just using, when I refer to f, it's going to be this function 1 minus 5x. All right, so filling in here, we want to take the derivative of f multiplied by g. That's how our product rule starts out. So the derivative of f is going to be 1 minus 5x. The derivative is going to be negative 5. And then we copy down g. So 1 plus 5x raised to the negative first power. And then we're supposed to add, we copy down f, 1 minus 5x, multiplied by the derivative of g. So the derivative of g is going to be a little bit more difficult in this case because we've rewritten it so you can see a negative exponent. So what we have going on here is going to be the chain rule, where we have a function, 1 plus 5x, inside of another function, basically something raised to the negative first power. So initially what we want to do is we want to take the derivative of the outer function and leave the inner function as is. And then we're going to multiply that by the derivative of the inner function. So taking the derivative of the outer function, something raised to the negative first power is going to be, you bring the negative 1 down. You're going to copy down what was on the inside, 1 plus 5x, and then you reduce the exponent by 1. So negative 1 minus 1 more makes negative 2. And then we need to multiply by the derivative of the inner function, the 1 plus 5x. So its derivative is going to be 5. All right, now comes basically some simplifying back down and seeing if we can combine anything together and make it look a little bit nicer. So I'm going to get rid of my negative exponents and rewrite this so it's all positive exponents. So we have negative 5 over 1 plus 5x raised to the positive first power. And then looking at what else we have going on the right-hand side, we have negative 1 times positive 5. I'm going to write that as minus 5. And then we already have a positive exponent here, so multiplied by 1 minus 5x. And in our denominator, we can get rid of our negative exponents and make this 1 plus 5x raised to the second power. All right, at this point, we don't quite have the common denominator. So I'm going to go ahead and make a common denominator. We're going to need 1 plus 5x squared for our common denominator. Well, on the first fraction over here, we have one copy of 1 plus 5x. We're going to need to multiply numerator and denominator by another copy of 1 plus 5x. All right, where that's going to land us is we can say we can distribute that negative 5 to each one of those terms in the 1 plus 5x. So that's negative 5 minus 25x all over 1 plus 5x squared. And then I'm also going to bring along my minus, and that 5 is going to get distributed to each one of these terms over here. So 5 minus 25x over 1 plus 5x quantity squared. All right, now that we have a common denominator, let's go ahead and put these numerators together over that common denominator. So 1 plus 5x is going to be 5x squared, I should say, is our common denominator. And we can say negative 5 minus 25x minus 5 plus 25x. So we want to be careful that because we have two terms in that second numerator, this is like a negative 1 that needs to be distributed to each one of them. Now let's combine together our like terms in our numerator. So we have negative 5 minus 5 more makes negative 10, but we also have negative 25 plus 25 negative 25x's plus 25x's get to cancel each other out. 1 plus 5x quantity squared. And there's our first derivative. Now, if we want to evaluate our first derivative at a given x value, say x equals 1, we're going to plug in 1 in for the x. All right, that gives us negative 10 over, let me see, 1 plus 5 times 1 is 1 plus 5 makes 6 squared. It's going to be negative 10 over 36, which is actually equal to, we can say it's exactly equal to 0.27 repeating. It's also equal to negative 5/18 in exact form, in lowest terms. All right, because that turns out being a negative, when we plugged in a 1 for our first derivative, that tells us that the entire graph is decreasing at an x value of 1. Now, if we want to find the second derivative, again, I'm going to visualize this as being a negative exponent. So this original, we took the first derivative, you can say that's negative 10 times 1 plus 5x to the negative second power. And again, go through and find the second derivative. This one's not going to be that bad, that we do have a nice constant. The negative 10 can come along. And then we're going to use the chain rule on the 1 plus 5x to the negative second power. So the negative 2 comes down. We're going to copy down what's on the inside, 1 plus 5x, the inner function, reduce the exponent by 1. So negative 2 minus 1 more makes negative 3. And then multiply by the derivative of the inner function. So the derivative of the inner function, 1 plus 5x, is just going to be 5. This gives us, as we multiply negative 10 times negative 2 times positive 5, positive 100 over 1 plus 5x to the positive third power. I went ahead and got rid of my negative exponent, move that back down to the denominator. All right, now let's evaluate this second derivative at an x value of 1. So the second derivative is plug in a 1 for our x and reduce this down a little bit. We get 100 over 6 to the third power, which is 100 over 216, which both multiples of 4 make 25/54, which is equal to positive 0.4629 repeating. Because that's positive in our second derivative, that tells us that the graph is concave up at an x value of 1. All right, hope this helps out. Sometimes you can use the quotient rule, obviously, when you have fractions like this, or you can rewrite it if you're more comfortable using the product rule. Sometimes that's just easier to visualize and memorize than the quotient rule. All right, hope this helps. Good luck to you on that.